Hello! Welcome to today's lesson on comparing types of radiation in terms of radiation damage. Our plan for this lesson is to begin by understanding the damage caused by alpha radiation, both inside the body and in laboratories. Next, we'll consider the risks associated with beta particles and how this compares with alpha radiation. Finally, we'll look at how gamma radiation causes damage and compare it with both alpha and beta radiation. So far, we have covered the basics of alpha, beta, and gamma radiation, including their associated nuclear equations. We also have a general understanding of the concept of radiation damage. Building on this foundation, we will now compare these types of radiation in terms of the damage they cause. This lesson will enhance our understanding of nuclear processes and the implications of radiation exposure in different environments. Let's explore how different types of radiation, alpha, beta, and gamma, affect living tissues and their potential health risks. Firstly, let's consider alpha radiation. To recap, an alpha particle is a helium-4 nucleus consisting of 2 protons and 2 neutrons. This gives it a relatively large mass compared to beta particles or gamma rays. We have learned that their high mass and charge makes alpha particles highly ionizing, meaning they can easily ionize or knock electrons off atoms they encounter in their path. This makes them particularly dangerous inside the body. Once inhaled or ingested, their high ionizing power can create significant chemical changes in cells, potentially leading to cancer or other health issues. Their low penetrating power means they cause intense localized damage within the tissues. However, while alpha radiation is highly dangerous inside the body, it poses less of a threat externally. Alpha particles can't travel more than a few centimeters in the air and are stopped by the outer layer of our skin. So, in a laboratory setting, alpha radiation is not a significant hazard as long as the particles do not enter the body. Next is beta particles. We have previously seen that beta particles are fast-moving electrons with moderate ionizing power and greater penetrating power than alpha particles. Beta particles can penetrate farther into tissues than alpha particles, but have a lower ionizing power. This means they can spread their energy over a large area, causing less damage to individual cells. However, they still pose a risk, particularly if they accumulate in bones or other tissues. Beta radiation can penetrate the skin, but it's generally stopped by clothing or a few millimeters of plastic. In a lab environment, appropriate safety measures such as wearing protective clothing can significantly reduce the risk posed by beta radiation. Finally, gamma rays. Gamma rays are massless, chargeless electromagnetic waves, and so they have the lowest ionizing power but the highest penetrating power among the 3 types of radiation. Gamma rays can penetrate deep into tissues, passing through cells and organs and spreading their energy throughout the body. Although their low penetrating power means they are less likely to cause immediate direct harm to individual cells, their ability to penetrate the body can lead to significant indirect damage which can cause long-term health effects, including cancer. Gamma rays are the most dangerous in a laboratory setting because they can travel considerable distances and penetrate most materials, including skin and clothes. Dense materials like lead or thick concrete are required to provide effective shielding. Therefore, extreme care must be taken when working with gamma radiation to protect oneself from exposure. In today's lesson, we compared alpha, beta, and gamma radiation in terms of their damage to living tissues and associated health risks. Understanding the distinct behaviors and dangers of these radiation types is essential for managing exposure risks effectively in medical and laboratory environments.